So hi everyone, this is the Scaling Ingest Pipelines with High Performance Computing Principles talk. My name is Rajiv, I'm a software engineer at SignalFx. So the agenda for today, we're gonna talk about what we mean by ingest and why we needed to scale it. We're gonna look at some properties and limitations of modern hardware. We're gonna look at some optimization techniques inspired by this knowledge of hardware. And we're gonna then look at some results by applying these techniques, and hopefully at the end we'll have some time for Q&A. So what do we mean by ingest? Before we can talk about that, let's talk about what SignalFx does. So SignalFx is a monitoring platform. We ingest high resolution time series data. We do streaming analytics on that data, so it's a soft real-time system. And we can do this analytics on multidimensional metrics. So you could do things like find the 99th percentile latency by service, by customer. So what is the ingest pipeline and where does it fit in? So the ingest pipeline is the part of the system which actually ingests this raw data. So it's built from a couple of systems. It does simple things like just ingest the data, do some rate control on it. We roll it up using some very simple time series math. And then we send it to downstream systems to be persisted and for real-time analytics. So the part we're going to talk about actually is the part in the middle, the part that actually does the math. So in abstract, it kind of looks like this, the library. We take raw time series data in. Every time series has some memory associated with it. We do some roll-up on that time series data. And then whenever required, we produce some data out. And that's it. So it's really simple. So why do we need to actually optimize such a simple service? Well, we had an existing service, and it was too expensive. It was too slow for what it did. It required too many servers. And again, time series processing is an embarrassingly parallel task. But we found out that as we added more threads, we actually slowed down. And what did the profile say? Well, there were no big hotspots that we could really focus our optimization efforts on. It was a death by 1,000 cuts. There was 1% here, 0.5% there. And everything together added up to around 35% of the entire server. The rest was in actually getting the data in and getting the data out and doing some other stuff that we're not going to talk about. So before we can talk about what kind of techniques we use, let's do a recap of modern hardware and how it works. So this is a very high-level diagram of a modern x86-like processing system. This is a single socket dual core. Usually we have multiple sockets and multiple cores on each socket. So a good way to think about modern processing systems is to treat them like distributed systems. So on one end, you have your fast number crunching cores, and on the other end, you have your main memory, which is supplying these cores. So over the past few decades or so, core speed started going up really, really high, and main memory was not able to keep up. So like all good distributed systems engineers, processor designers decided to add a bunch of caches in the middle. And a good rule of thumb is as caches get closer to a core, they get faster. They also get smaller. So the faster a cache is, the smaller it is. So L1, L2, and L3 are caches at different levels. L1 is usually the cache closest to the core. It's usually segregated into data and instructions. Then you have L2, which is still core local, and it is not segregated into data and instructions. Then you have level 3, or the last level cache. Sometimes some processors have a L4, which is a level 4. Either way, it's usually shared by all cores in that socket. So a misbehaving application running on core 2 could easily affect a well-behaved one running on core 1. So let's talk about cache lines. So when data is transferred between memory and caches, it's never done a byte at a time. It's done in fixed size blocks called cache lines, usually 64 bytes on most x86 machines. So when the processor needs to read or write a location in main memory, it first checks for its presence in the cache. If it's there, it's a hit, and the write is immediate. If it's not, then the cache allocates an entry. It needs to page that entry in from main memory, and then the request is fulfilled from the cache. So as you can see, this is a much slower process. So this is a pretty complicated system, and processor designers kind of make two bets to help us. One is temporal locality, the other is spatial. So temporal locality really says that if you have some piece of data that you've accessed, you're very likely to access it again in the near future. Spatial locality says that if you've accessed some piece of data, you're very likely to access some other piece of data really close to it in memory. Spatial locality kind of has another dimension. If you have predictable access patterns while paging through memory, the processor can actually hide those cache misses by prefetching data for you. So things like walking linearly through an array or walking linearly with a little bit of a stride, the processor can actually detect these patterns and prefetch all this data for you. So it's really good. On the other end, if you do random walks through memory, the processor has no way to figure that out, and you actually go through the expensive path, which is a cache miss. So this is a chart that shows the relative speeds of main memory and caches, courtesy of Jeff Dean at Google. So the numbers are not that important. What's really important is main memory can be up to 200 times slower than your L1 cache. So just to drive that point home, here's a little animation. So let's imagine that on the left you have some piece of data in your L1 cache, and it's trying to get to your core for some processing. So let's imagine that this is the speed with which it gets there. So that's pretty fast. Now let's imagine that the same data is in your L2. So that's how fast it is. So it's still pretty fast. I've dedicated around 95% of my presentation time on this one slide. So this is the same piece of data getting from main memory to core. That's actually how slow it is. So all the old advice around avoiding instructions like divisions or square root because they're expensive, they're kind of second-order effects in the world that we live in. This main memory slowness, it's almost like disk, is what we're really trying to avoid. So let's wait for that to finish. All right. So knowing what we know about hardware, our goal, and as it should be for most applications, is to convert a memory bandwidth-bound application to a CPU-bound application. Because our processors are just so fast, we just can't keep up. So things we kept in mind when we went on this exercise, we always measured. And also, we didn't rely on micro benchmarks. We tried to measure our own application. So really, that's the best way to kind of see progress as you're making changes. And we talked about how micro benchmarks are evil. So let's talk about a micro benchmark that we're going to actually use for the rest of the presentation, contradict ourselves a little bit. So this is the micro benchmark that we are going to use for the rest of the presentation. So really, like we said in abstract, our time series are keyed by ID. It's a 64-bit ID. And there's some data. It's not really important what it is for each time series. So for our micro benchmark, we have 1 million of these time series. And we send data in one data point per time series in random order, so a little realistic. And we repeat it 50 times, and then we take a percentile on how much time it took to process this, and that's our benchmark. So it's around 50 million points getting in. Just to remind everyone, this was only 35% of the actual application. So we were optimizing something which was only 35%. So let's look at some of the techniques that we actually used. So before we went on this exercise, our application was concurrent. It used concurrent data structures everywhere. So we converted it to a single-threaded event-based architecture. And again, time series processing is embarrassingly parallel, so it was easy to run multiple copies of the same code on separate threads to actually get all the parallelism that we could. So what do we mean by single-threaded event-based architectures? Well, threads work on their own private data. They don't share anything with other threads as much as possible. And when they do have to communicate with other threads, they do that using events or messages and not shared data structures. So this is really our canonical example diagram for an event-based architecture. You have one network thread that receives data, parses it, validates it, creates events out of it, sends it to a processor thread. The processor thread processes it using only local data. Sometimes it needs to send data back or to downstream services, so it sends them as events. Then your network out thread batches these events, because again, it's a single thread, it can batch really well, and sends them out. So we added another refinement to that architecture. So when we need to send events across threads, we use fixed-size circular buffers or ring buffers. So ring buffers, again, are just arrays. And like we talked about, arrays are really good for the processor. It's a fixed amount of memory, so we're reusing it over and over again. So spatial locality-wise, this does really well. And on x86, it is actually really easy to write these very efficiently when you have a single producer and single consumer. So we can do more than 400 or 500 million events per second between two threads using simple ring buffers. So why single-threaded event-based architectures? So obviously, locks are gone. That's a big advantage. But the biggest advantage is actually that single-threaded event-based architectures are like inlining in a compiler. They're a gateway drug. They really help you do other optimizations much better. So now that you're single-threaded, it's very easy to use array-based data structures instead of pointer-based ones. Most concurrent data structures have a lot of allocation. They're all pointer-based because it's easy to write them that way. When you're single-threaded, it's just really easy to write array-based data structures instead. Since they're single-threaded, you can reason about the lifetime of objects. So it's really easy to reuse buffers, reuse objects over and over again instead of allocating them. They're easy to test. You could just replace the network in and network out thread with test threads, and the business logic is just very easy to test. And again, you can run multiple copies for parallelism. So let's look at a few flavors of event-based architectures. We'll cover a few. There are obviously many, many more possible. We already looked at this one. So let's look at another one. So here, really, workers are completely independent. There's no communication at all. And this is really a shared nothing approach, and this is really the fastest you can get. It's a very good match if you are doing stateless processing. Let's say you have an image processing server, data comes in, you process the image, you send it out. So you're always working with hot data in your caches, and there's no communication at all. So here's a slightly more complex setup. So again, you have your network in thread. It gets data. It sends it via a ring buffer to a processor thread. The processor thread tries to process it synchronously. If it can't, sometimes it needs, let's say, external resources. So it just stashes that data when that happens, and it sends a request to another thread, which will do the I/O for it, and it moves on. It's not paused at any time. This async I/O thread will batch a lot of these requests and make a big batch call. Once the results come back, it's going to send them back to the thread that requested it. And then that little data point that it had stashed is going to pick it up and continue processing. So the processor thread was never, ever blocked on I/O. It just kept moving on. A little tricky thing here is that we have circular communication between the processor threads and I/O threads. And when we use fixed-size buffers, there's a chance of a deadlock. So you have to be a little careful. There are many tricks that you can do to avoid these deadlocks, but we're not going to talk about them. So some last moment advice for threaded applications. Thread should ideally reflect the actual parallelism of the system. So instead of having a thread per client or a thread per job or anything like that, ideally we have threads, one thread for each core. So what about I/O threads and legacy systems? Well, we can't really avoid those in most systems. So a good way to deal with them is to put them in their own little thread pool and make sure that it gets scheduled maybe on a single core, so you don't pollute your other cores with this I/O workload. And we saw that you can send like upwards of 400 or 500 million events per second on a ring buffer, but even then it is best not to communicate. So only communicate if you have to, and good designs can go all the way from the client to the server without any communication, just a straight pipe. So we talked about single-threaded architectures. Let's really talk about what it enables, which is compact, cache-conscious, array-based data structures instead of pointer ones. So just to recap again, we already looked at this, but the faster a cache is, the smaller it is. So that's just something to keep in mind. So how do you design data structures that are really fast? Well, the smaller a data structure is, the more of it can fit in the cache, and the faster it is, really. Even if it is at the cost of some extra computation, like processors, again, are very good at doing stuff like bit fiddling. So if you can use some of that to Shrink your data structures, that's totally fine. This is exactly like compressing network data. Their network bandwidth is your limited resource. Your memory bandwidth is a limited resource. So we should design data structures that facilitate processing multiple entries. What do I mean by that? We rarely ever process one of anything. It's always multiple HTTP requests, multiple points in a time series database, multiple objects in an animation frame of a game. So just being cognizant of the fact that we process multiple things together opens up a lot of opportunities for optimization. And we'll look at some of those later. Layout should reflect actual access patterns. So again, because of spatial locality, things that are accessed together should be together in memory, even if they logically belong in different objects. Things that are not accessed together should be far away in memory too, even though they logically belong in the same object. So let's look at an example of applying these principles to a hash map. Now, every other line in our code is a hash map get or a put. And we've been told that hash map lookups are free. They're not free. A hash map lookup, by definition, is a cache miss. And why is that? Well, because the first thing you do is you hash your key, you land on a random index in an array, maybe. Random things are very bad. So that is a cache miss waiting to happen right there. But popular implementations like Java's hash map or C++'s hash map, the standard ones, can actually cause multiple cache misses. So let's trace a simple get operation in a hash map designed as a list of key value pointers, or an array of a list of key value pointers. This is actually pretty much the exact design of Java's hash map and very similar to C++'s. So the first thing you do is you get your key, you hash it, you land on a random index. Let's assume it's this one. That's a cache miss because it's a random index. The processor had no way to predict where you'd land. This is a list, so you have to follow a pointer. A pointer is, again, a random pointer, another cache miss. Now you need to check if your key is actually equal to the one you were searching for. You need to go another pointer, that's another cache miss. Let's imagine that this was a hit. So you return the value pointer, and then whoever called you needs to dereference that pointer to actually get the value. That's another cache miss. So cache misses for everyone. So there's almost no good reason to use this data structure, or rather this implementation of a hash map. It's a slightly better implementation. So we have one big array here, and key and values, let's assume they're small. Let's say it's a 64-bit key and say a 32-bit value. They're laid out next to each other in memory. So it's one array, so you have key 0, then value 0, key 1, then value 1. Let's trace and you can use things like linear probing or other probing methods to resolve collisions, but we're not going to get into those details. Let's just assume we use linear probing here. So let's trace that same get operation. You hash your key, cache miss, because you land on a random index. And no hash map can really prevent this first cache miss. But now, key 1 and value 1 were right next to each other. And so in that one cache miss, you have actually gotten all the data that you really needed, if this was a hit. Let's assume it was. So now let's assume the values are actually really big. Say they occupy multiple cache lines. And we actually have collisions for a change. So let's imagine we're trying to find key 3 in a hash map where values are actually really big. So again, we do this hash map, and let's assume it lands on the same index. That's a cache miss. You don't find it there, so you need to look at the next one. But value 1 was just so big that key 2 is most likely in another cache line. So another cache miss. But this is, again, not the thing you were looking for. So you look at the next thing. Finally, you get key 3. That was yet another cache miss. So this kind of hash map is really good if you don't have too many collisions or if your key and values are small. But if your values especially start getting big and you have more collisions, you might have to pay for a lot of cache misses. So here's another variation of the same hash map. Here, we assume that our values are really big. So we actually store them on the side in one big giant array where they're right next to each other. And our hash map on the left is exactly the hash map we looked before. But now it's a hash map from a key, which is, let's say, 64 bits again, and our index, which is a 32-bit index to this array. So now our key and value put together is 12 bytes. So given that we have 64-byte cache lines, 5 of these can fit in a single cache line. So let's trace that same colliding key get operation. So again, we are looking to get key 3, but it hashes on the same slot as key 1. So we land on key 1. That's a cache miss. We know that we can't avoid that. But given that 5 of these entries fit in the same cache line, there's a very good chance that key 3 actually came along for the ride when you pulled in this cache line. So you look at key 2, it's probably in the same cache line, no cache miss. You look at key 3, it's in the same cache line. So these lookups are very cheap. It's the cache fetches which are expensive, but you haven't paid anything beyond that one cache miss. So we found key 3, but now to get to the value, we need to follow that pointer. That's another cache miss. But now we've kind of bounded to 2 cache misses. So in the best case, we always have to pay 2 cache misses. But most of the times, even in the worst case, it is 2 cache misses. So this is a slightly better design, especially if your values are really, really big. Your keys still need to be small. So for our library, we've actually used pretty much the exact layout. We have a hash map of indexes or keys to indexes where these indexes point to time series data. These time series data are fixed size, and they're multiple cache lines big, actually. So our previous layout or implementation, which we're not going to talk about much, was written with very much of an object-oriented style where every little module was in its own little object, a pointer away, and each was fronted by its own hash map. So this is a lot better. There's a single hash map, and all the data is in one place, really taking advantage of that spatial locality. So on our already optimized layout, the only change we've done for this one benchmark that we're going to talk about is change the hash map on the left from Java utils hash map to an open hash map like the one we talked about in the beginning, where keys and values are laid out right next to each other. So that change alone netted us a 45% improvement. So if there's one thing you can take away from this talk is if you have hash maps which have primitive keys and values, please don't use Java's or C++'s hash map. There are better alternatives. C++ especially, it's very easy to roll up your own ones, or there are a bunch of examples on GitHub. Here are a couple. Now let's talk about access patterns. So we've talked about spatial locality quite a bit. This is another example where it matters. So let's say we have objects with 5 fields, and we worked really hard to put all 5 fields in a single cache line, so it's less than 64 bytes. And we've laid these objects out in a contiguous array because processors love arrays, big arrays. And now we have a hot loop running and only going through the first 3 fields of every object, but all the objects. So that's the hot data, the first 3 fields. But because of how cache lines work, every time we fetch fields 0, 1, and 2, 3 and 4 come along for the ride, and we don't do anything useful with it. We discard it immediately. So we have around a 40% waste here in the data that we're getting in. A better layout, given how we're accessing our data, is this. We separate the hot fields into their own array, the cold fields into their own array, and your object virtually points to the hot array and the cold array. When you need the hot fields, get it from the top array. When you need the cold fields, get it from the bottom. So now that same loop that we had going through only the hot fields, now all the data that it's getting in is from the top array, so we're not wasting anything. Everything is actually being used. So we actually applied this principle in our own application. We had a hot run loop that runs every 500 milliseconds, and before we separated the hot and cold data, our time series data was 5 cache lines big. Once we separated it, it was 3 cache lines of hot data, and the rest was cold, kept somewhere on the side. And we made a 35% improvement of the potential 40% that we could have made. And this is, again, on a very optimized application. So this was a very, very easy win. So again, just to recap, by acknowledging the fact that we were processing multiple entries at the same time, it was really easy to look at this access patterns. If you had gone the typical object-oriented programming route, we would have stuck with this and said, OK, let's put a few getters and setters. This exists in its own vacuum. And we would have not seen this optimization opportunity. But by knowing that we access a lot of them together, it was easy to see that the hot data should have been separated. Kind of goes against a little OOP programming, but really made a difference. So let's look at the results of applying these techniques on our own library. So just a recap, we went from concurrent to single-threaded. That really helped us. Obviously, the locks were gone, but the bigger changes were that we had array-based data structures. Because we could reason about lifetimes of objects, we had actually exactly 0 allocations in the data path. And we had extensive batching and prefetching opportunities just because we laid out everything in arrays. And we went from multiple hash maps to a single hash map lookup. So hash map lookups are killers. They kill your performance, especially if you're trying to do numerical work. So the fewer, the better. So here are a couple of screenshots of running our benchmark. This is a screenshot from this application called JVisualVM, which you can use to monitor your JVM-based applications. So we have a couple charts. The one on the top is our old application. The one on the bottom is the new one. And it's running the same benchmark that we talked about before. The charts on the left are CPU. The charts on the right are heap. So you can see the top chart, CPU is all over the place as we ran the benchmark. Goes to above 80% many times. Heap is all over the place, even though we're only processing 1 million time series, not that much data. And we pay for a lot of garbage collection. The bottom is a lot better. It's steady at 12.5%. You can see a slight little ramp in the beginning. That's when we allocate everything. And it's all pre-allocated, so there's like really no heap churn. And again, just because we were able to shrink the data so much, most of the things actually fit in cache. So the top one did around 76,000 data points per second. The bottom one did 2.1 million data points per second. So that's a 27 times improvement just by arranging our data structures better. There was no change at all in how we did the math. There's no smarter math. It was very dumb math, just the data structures change. But remember, this was 27x on something which was only 35% of the profile. So how did we do in the actual application? So all we did was change the library from this bad one to the new hot one. So the green, this is only our CPU usage. The green is our old one. It's running at 50%. The brown is the new one, running at around 12.5 to 13%. CPU, and they're getting pretty much the same amount of data points. And the brown one, actually, if I remember, the new one got a little bit more. But they're pretty much identical. And you can see the patterns are also very similar because it was just getting teed off. So that's around a 3.8x improvement by working on something which was just 35% of the profile. So how is that even possible? How could you optimize something? Even if you take that whole 35%, you shouldn't be able to see so much improvement. Also, profilers lie all the time. It's an important tool, but not a substitute for informed design, especially if you have a profile which tells you that you have 1% here and 0.5% there. It's not going to be very accurate. What you really need to look at is tools like perf, where you see how many cache misses you have. And even then, it won't point you exactly where you have the cache misses. Some profilers are capable, some less so. But you really need to look at your data structures and use first principles to decide how to make them better. The second thing is caches are shared resources, like we talked about before. So when you use less cache, you leave more for others to use. So you speed them up too. And when you use more cache, you have less for others, so you slow them down too. So there's this really non-intuitive relationship here. So here is heap growth. The brown is the new one, the green is the old one. So we said that we were 0 allocation, but clearly you can see our heap is growing because, well, the 65% of the other data that is, or code that is running actually does allocations. But it's still, like you can see, we garbage collect a lot less often. So a little bit of a rant at the end. In our industry, we're always told that write code first, profile later. But when you want to make things fast, this is usually not the best way to go around. And if you remember, like most of the techniques that we talked about today were actually all design time techniques. They were not some magic math optimization. It was stuff like reasoning about your access patterns, reasoning about object lifetimes. And not only do they lead to faster code, they many times lead to better programs because you understand your problem a lot better. And in my experience, at least, profiling badly written programs and then trying to improve them leads to a slightly better version of what is still a badly written program. So thinking about performance from the get-go when you're designing is usually the best way to get fast code. Second point, a little bit of a rant against object-oriented programming. So this works for the most part, but object-oriented programming leads to myopic decisions being made, especially when it comes to performance. We just don't know how our libraries are going to be used, so we make them super generic. We do allocations because we don't know the lifetime of the objects that we're returning. We do write thread-safe code because we don't know what threads our library is going to be called from. So we make a lot of low-level decisions in a place where we really don't have enough knowledge. So again, you can go like write everything custom data structures, custom algorithms, and that's probably not tenable. But on the other extreme, writing just code with off-the-shelf data structures usually is not the best way. Just a little bit of thought ahead of time to see how your code fits in together usually pays very rich dividends. So we talked about a micro-benchmark the whole talk, but micro-benchmarks are very, very evil, especially on complex runtimes like JVM. The compiler will optimize all kinds of things for you, and your micro-benchmark might not be even running the code that you really think it's running. It's also really difficult to get realistic data patterns. So teeing off customer data is a very good way. But really the best way we found is actually measuring on your real application and run real customer data through it, see how our application changes, and that's really your yardstick. So that's really my talk. I hope you'll be able to use some of these techniques in your own work and get some performance gains. So here's my contact. We're hiring if you like work like this. We have a lot more. So I'll take some questions now, if you have any. Yeah, good. Right. Right. Yeah. Yeah, definitely. So I haven't worked so much with Node.js, but I know V8, the compiler, which I've worked on before actually, does a lot of optimization. So one of the optimizations that it does is it tries to figure out the shape of your object, and it actually tries to make a struct or a class from it. So as long as you have objects which don't change shape very often, where you have, say you have 3 fields, A, B, and C, and they're integers, the compiler will realize, the JIT will realize that that is your object, and it will make a little class out of it and actually generate properly optimized code as if it was a class in Java or C++, almost. So as long as you don't keep changing the shape, you should be actually really good. V8 will give you pretty good performance. So I think the biggest thing when you're working in dynamic languages is to actually treat them as static languages. Like if you have a class, don't change it. Don't treat it as a hash map where you can make keys and values. Treat it as a struct. Treat it as a class, and the compiler will do its job. And for numbers, if you're dealing with numbers, JavaScript especially now has actually typed arrays, which do numbers natively. So the code generated there is very, very efficient, almost as good as C++. So use those if you really have a bottleneck. But just keeping static shapes in your classes is already a very good first step. Anything else?
You mentioned using perf. Does that actually give you process-level cache statistics?
Yes, it does. So yeah, it'll give you things like cache misses, branch predictions that went wrong. We haven't talked about branch predictions, but that's another place where your cache can get, that's your code cache, which is really getting, because x86 processors especially are pipeline. So if you have branches that are not predictable, your pipeline needs to get flushed, which is a total mess. So it'll give you that kind of statistics, actually.
You would benchmark at the application level, but you were actually doing perf runs and making sure the decisions you're making
Yeah.
didn't manage cache optimization.
Right. So perf is a tool where personally, I think it's very difficult to say that this part of your code is wrong. You can just tell that it's wrong. So you can compare a couple things instead of really pointing out that, okay, this is where it's going wrong. So we usually run perf after making a change to see, okay, I thought that this should reduce the amount of cache misses. Has it really reduced the amount of cache misses? Yes, it has, or no. Okay, let's go back to the drawing board. Right.
And you said that it makes sense to actually set the core affinity for that type of thread.
Right.
Do you actually do that, and have you seen that?
Yes, we have. So Linux is especially really, really good at this already. So throughput-wise, I don't think you'll see a big difference. Jitter-wise, you'll see a big difference. Because once that thread goes, its cache is gone. It's totally destroyed. So you'll see that sudden, like, you're hitting latencies of, say, a few nanoseconds, and suddenly you have that big hit where you actually had a cache miss. Everything gets paged in again. But soon you'll be back to the same throughput. But latency-wise or jitter-wise, it makes a big difference. Yeah, especially on IO systems, if you're using things like custom networking stacks, which almost no one does. But this is one of the big factors. Like, you can get a massive difference in latency just from doing that. And there are tools even in high-level languages like Java, which will let you pin a thread to a core. They use JNI, but we don't need to know that. Yeah, please. Right. I'm sorry, could you repeat that? Right. 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 Right, right. So the question was around whether we need to think about object sizes right from the get-go. Usually I don't. Like, just by starting with keeping the domain model really clean goes a really long way. I usually start thinking about that when I try and start the actual implementation. But thinking about the actual access patterns, like the hot loop, run loop example that I gave, knowing that we have this hot loop which will run through but only access a few things already gives me, I just make a little note and I know that at some time, separating these will actually lead to a benefit. You don't need to do it right off the bat. We didn't. But a 35% gain is nothing to laugh at. But yes, like, just knowing your access patterns, writing them down, you're very clear on them, then it's easy to design data structures. You can start with a more sloppy approach and then iterate and make it better. But with object-oriented programming especially, it's really, really easy to like get into this object hierarchy, which ultimately ends up being very inflexible, and then you can't budge from it. So it's good to not like corner yourself that way and keep that option open for the future. And just again, like cache size, like object sizes, sometimes you can't do much about it. We have data sizes which are like 3 cache lines, and there's like almost nothing we can do to reduce that size. But already just keeping it all together instead of in Java, like if you have a class made out of 5 different classes, they're all pointers and they're all over the place. And knowing this, so Java's abstractions are not free. In C++ or C, they kind of are. So just being cognizant of the fact that all of this will be used together, you can again start with something where you refactor them, but when it comes time, you should be able to fold them back in if your abstractions are clean enough. So I don't know if that answers your question. Anything else? Good. Well, thank you, everyone.